All right, morning everyone. My name is Noman Mithani. I'm a mechanical engineer at Meta, and together with our team at Meta and industry partners, we've been working on a specification for large dripless interoperable quick connectors. So in this presentation, we're going to talk about, or I'm going to talk about, the need that the market has for these quick connectors and how we use our general use cases to come up with a set of goals and requirements to design around. And then I'll talk about a couple rounds of testing and prototyping that we've done and where we are today, which is a almost mature design that we're ready to build a specification around. So the partners we've been working with, there's similar partners that you just heard about from the Blind Mate connectors, Sen, Parker, and Safeway. And they've been really instrumental in taking their deep knowledge of fluid connectors, products that they already have in the industry right now, and adapting that for a general purpose, interoperable, open source design. And we've actually been able to improve on existing products in the market, and so we're really excited to show what we've been up to. So the overall goal of this interoperable large dripless quick connector is we wanted to create a spec that can be made by multiple vendors, be open sourced, and then any vendor on the market can produce this and sell to the community. There are interoperable quick connectors that exist on the market and even contributed to OCP, but they're all at the IT gear chassis level body size. And there's even some that are smaller that are better use for air vents or fill drain ports or small use cases. So we haven't seen a large quick connector that's interoperable on the market that exists today. And so that's what we've set out to design. Like the other Blind Mate and other OCP quick connectors, we wanted to maintain vendor-specific inner valve designs. So their secret sauce they can keep to themselves, but we would define the bare minimum needed to connect different parts together. So a socket from vendor A to a plug and vendor B. They should both flawlessly work together and have consistent performance. And then they should all bait easily as well. So some of the general use cases that we have for these large quick connectors, and that's represented by the yellow valves in the diagrams. The simplest is you're connecting an IT rack with hot and cold manifolds to facility plumbing. That's kind of where we see most of the industry going in the future. But before that adoption happens, there's a lot of other use cases that we can use this for. So for example, if there's a CDU or coolant distribution unit within a rack, and as well as rack manifolds, those can be connected together then to the facility with these quick connectors. Or if there's other all-in-one solutions, so like the air-assisted liquid cooling rack that we have in our Meta booth, we have multiple connections that take a heat exchanger, manifolds, and a reservoir and pumping unit, and all of those are connected with large quick connectors. So you can see the quantity can really add up, and as liquid cooling adoption increases, we really see this scale increasing. So we took those general use cases I just described and created a basic set of requirements around that. We started off with a 1-inch flow diameter. That's usually the kind of flow diameter that can provide the rated flow rate that we would want for these applications. But we wanted to have the headroom for it to go up to maybe an upper target of 100 plus LPM. They had to be dripless and able to mate under pressure. So whether you're mating for the first time dry in a data center, or if you're replacing a rack that is in a row that's already been energized and filled with coolant, you should be able to connect these dripless and easily. Since all of this is going to be integrated into the same supply chain and the same racks that are shipped, we wanted to make sure that all of these components are falling within the same data center, shipping, and storage conditions and tests. So there's temperature, there's pressure, humidity, a whole full range of tests. as well as having a max pressure requirement that is well above the rated use case. So plenty of margin left on the table. And then the main thing is they have to be interoperable. So we're sharing the internal valve and the outer mating mechanism. So there's valve dimensions, there's the mating threads for how these connect to each other, and then a shared wetted materials list so that there's chemical compatibility between any vendor parts. And then the main thing that we're actually trying to improve is ease of use. So most quick connectors on the market today, they are push to connect with the sliding sleeve, and those work great for small body sizes, especially for IT gear level connections. But when you scale that mechanism to a 1-inch, 3/4-inch type design, the mate forces increase dramatically. And if you can imagine a data center with thousands of racks that are liquid cooled and multiple connections per rack, that can really become a pain point and stopping capacity from getting deployed quickly. So what we really want to focus on with these is very low mate torque. So instead of a push to connect, we went with a twist to lock design, where there's a sleeve that can twist over the plug. And we wanted to make sure that all of this is ergonomic. So we conducted some tests to make sure we're falling within a maximum mate torque, as well as making sure that the design, the footprint is shrunk down as much as we can so that it fits in various environments and orientations. So we took that basic requirements and first go at the design and created a round one. And so you can see on the right-hand picture, that's one of the samples from our partners. And then the picture next to it is a test fixture that we created at Meta to test both the flow impedance as well as the mate torque for all of the valve combinations. The overall results were that most valves were able to meet our initial performance and impedance targets. There's definitely room for improvement, and there were small fixes that we could make to the internal valve geometry that could get us there. The main issue actually was that mating and high torque was seen. So the thing that we're trying to improve on the most is we saw some binding and high mate torque to connect these, especially when you're connecting different vendor parts together. So that's something that we really wanted to improve on. But ultimately, no leaks or failures found, so the base technology is robust enough with all of our partners. The lessons learned going into the next round was we really needed to define the thread profile. So that's the thread that connects the plug to socket to each other with the rotating sleeve. So we needed to define that closely for easier mating, as well as the end terminations. So that's the internal thread that's on both ends of the plug-in socket. That needed to be defined as well, and we used an ISO spec to make sure that you can connect any barb fitting or elbow adapter or rigid pipe to any of these parts. We also updated material choices. So the wetted materials list stayed the same, but some of the non-wetted materials we can change to decrease friction, reduce galling, and just overall ease of manufacturing. And because we saw some room for improvement, we actually increased our performance targets. We are really happy with how our partners have been able to push their designs to really be better than existing products on the market today. So just a summary of the design changes for round two. There's an internal and external Acme thread that's the mating mechanism between the two parts. So that was more tightly defined. And then a blunt start was added to prevent binding, especially between different vendor valves. Like I mentioned, the end termination internal thread was defined so that the end user is able to install in fitting of their choice. And then the sleeve material, we actually changed from stainless steel to plated steel so that there's less galling and really reduce the friction on the rubbing parts. So this is where we come up with our round two prototypes and testing. So that's what's shown on the right. And overall, we're really pleased with the results. The biggest improvement is ease of mating. The improved thread design allowed us to have very smooth mating between the socket and plug, for both same vendor and cross-pollination combinations. And all the combinations, mate torque falls below our ergonomic targets. We tested a mate torque versus mate distance, and we're able to see a curve of how that mate torque changes as you're connecting parts together, both at dry conditions as well as if one side or the other were pressurized in operating conditions. We saw much more consistent flow performance, so all vendors are showing much closer grouping of flow versus pressure drop across multiple pairs compared to round one, so that was very good to see. And then we verified that the end terminations, a 1-inch BSP thread, was consistent across all vendors. So going into a little bit more detail in the flow performance testing, all valve combinations, so same vendor, plug-in socket plus cross-pollination, were tested for flow performance up to 100 LPM with propylene glycol 25 at 40 C. So that's a bit of our elevated temperature and pressure requirements, and we tested at both different pressure points, so maybe at 0 PSI all the way up to 40 PSI. And the overall performance is pretty good. For most combinations, they fall within our target range, so that's that green region on that chart. And you can see that for most data sets below 60 LPM, most combinations fall within that range, but as you get up to the upper targets, some data points are outside of that. So there are small changes that we can make that we're hoping that all data points can be within our target range. Next steps after round 2 is we do want to harmonize some more dimensions. So there's some hex dimensions on the end that we can have the same between all vendors. There's slight optimizations that the vendors can make to their inner valve to fall within the performance spec. And then we can further define thread surface finish and post-treatment for consistency, so even lower mate torque from before. Next steps for our overall team is we're finishing up the round 2 samples and validating the performance of those. And then taking that mature design, we're going to start a detailed specification that we can eventually contribute to OCP towards the end of this year. And we're hoping to take that to volume production next year. If you'd like to learn more, you can join the wiki and the mailing list for cooling environments and advanced cooling. Thank you so much.